Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day, inside my virtual classroom. Nearing the very end of the year, this is my last unit exam for my integrated math 2, folks, working on things involving similarity of triangles, right triangles, and trigonometry, and things like that. This is a practice exam, if you will. I believe there are 30 questions total. Now, some of them come in the same form of things, so after I kind of teach one of them, maybe it explains the other ones. And I'm going to come from a basis that maybe you've seen some of my other videos, meaning although I might give you a formula with it, I'm not going to give you the end-all be-all wherewithal of every little nitty-bitty bit of a problem. Well, it all depends. Maybe you'll see me say, or you can do a problem like this. Now, I like to do my little tips and tricks of reducing fractions and, things like that along the way, and I won't use a calculator unless I absolutely have to. So without further ado, guys, let's go ahead and get into it. I have not even taken my own practice test. It's not really mine. It's kind of my department's. But I added a couple problems here and there to kind of even it out. But let's get started right here on question number 1. If quadrilateral ABCD is similar to quadrilateral ZYXW, what segment corresponds with segment CA? Now, the important thing when it comes to a similarity statement or a congruence statement is that the ordering of the letter is all too important. Obviously, this is normal alphabetical order. This appears to be reverse alphabetical order. No matter. What matters is A is the first letter, B is the second, C is the third, D is the fourth, Z is the first letter, Y is the second, X is the third, and W is the fourth in this one right here. So to find out which segment corresponds with CA, CA isn't even a segment, I should say, when it comes to quadrilateral. I really should say what diagonal. This is obviously my own question where I don't look at this very deep enough. Because if I draw this ABCD, A and C don't actually even connect. So I'm looking at this, see, literally, even right now as I start this thing, what diagonal corresponds with it? How about that? That sounds a lot better. My apologies to my own students with that. The point is, what letters should belong? And it really has to do with C being the third letter, A being the first letter. Well, the third letter here is X, and the first letter here is Z. So we should say the answer is segment XZ. It's a segment in that it's not a side of this object that would correspond with this, but it is a diagonal, if you will. So my bad when it comes to that. But yeah, hey, without a drawing, even though they're similar. Are they congruent? No, probably not. When it comes to similarity, one figure is probably bigger than the others. They're not congruent, but they correspond. They still create a similarity ratio, even as non-sides. They still create a similarity ratio that corresponds with them, which we get to talk about in some of the next problems here. At least numbers 2 through 5, apparently. All right, numbers 2 through 5. State if the triangles are similar. If so, state how you know and complete the similarity statement. So we need to see if triangle ABC is similar to some other triangle here, and we're going to use either side, 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 similarity, side, angle, side, similarity, or angle, angle, similarity. Any of these will work. Now, when it comes to angle, angle, we need two sets of angles that will be congruent. I cannot get that here. I can get one set of angles that are congruent. If you guys notice here, there are two triangles. There's triangle ABC, the big guy. And there's the small one right here, which is triangle AUV. We're really trying to see if those two things are similar. Now, as those two separate triangles, guys, understand that they both share that angle A. You see how purple's going to join in? They share this angle A. That's something called the reflexive property that shows that angle A in one triangle is congruent to angle A in the other triangle. So I do have a set of angles that are congruent. Again, the A in the small and the A in the big by the reflexive property. That's good. But I can't get another set of angles congruent here. I don't know these lines are parallel, so I can't speak on corresponding angles. So my best hope really is to go for the side angle side principle, especially since the third set of sides are completely unknown. Totally not drawn to scale, as that's 9 and that's 27. But either way, what we can see is, does the length of AU compare to the length of AB in such a way that the length of AV compares to the length of AC. We're setting up a proportion to see if the similarity ratio is intact for both. And as both of them are 9 over 27 and 9 over 27, clearly those are equal, or a similarity ratio of 1 to 3. Hold on, something's happening with my screen here. There we go. Some little glitching out there. So 1 to 3, 1 to 3, whatever that thing checks out. So sides are proportional. The included angle, the angle in between is congruent. That is a side angle side case where triangle ABC is indeed similar to triangle AUV, ABC, AUV. And I guess AVU could work because there's still 9 and 27 for both sets, but AUV there. This is by side angle side right there. Now this continues with all the other problems here. Let's take a look at some of the others. Now, just to keep in mind as we're doing this, I'm going to kind of redraw that smaller, bigger triangle again. Make sure that you get what's going on here. Because just in case, I don't think another, well, we'll see if another problem ends up kind of being more confusing. But notice here, if I draw these separately and kind of label them up, we have this little side length here that's 30, this is 18, and this is 24. And then this side length right here is 50 and 40 and 30. Actually, I think that's even a right triangle. 3, 4, 5, special right triangle. So when you're setting up these proportions, understand that each thing seems to be doing whole side in one is to whole side in the other. This could have easily got a different route. This might not have, they might not have put 50 here, they might have put 20. And you have to be very careful what you put when it comes to setting up a proportion, because 30 to 20 is not whole side of one to whole side of another. So anyway, just be careful if we run into some of those. These ones are all set up in such a way that we are trying to find parts that correspond based on the reflexive property, knowing that's congruent. We could definitely do side angle side. I'm going to try and test the side thing because all the numbers are here though. Let's see if all parts correspond and are proportional. So I'm going to try 30 over 50 right here, 30 over 50 with this side and this side, 24 over 40. I'm going small to big with 18, excuse me, 18 over 30. Let's reduce these fractions and see what we get. 30 over 50 is 3/5. If I divide 24 and 40 both by 8, I do get 3/5 as well. And 18 divided by 30, if I divide those by 6, I also get 3/5. So all these check out as far as falling in proportion with one another, all three sets of sides. So it looks like by side, or side angle side, if you show that angle C is congruent to itself, that triangle CBA is similar to triangle apparently CKJ by side. Again, this goes back to, hopefully you've seen this stuff before, because if this is your first time seeing it, I can see why it would be very confusing. So side similarity. All right, let's keep moving forward here. Number 4, instead of having numbers, looks like we're going to test a little more for angle in this case here. Now, I do have a set of vertical angles that I could mark congruent here. Oh, I have to be careful. That is a single arc mark. I got to give a double. Oh, that is a double. That's triple. Let's do unique, quadruple arc marks there. That sounds good. These are congruent to each other because they are vertical angles. So that is one set of angles congruent. Angle, and do we have another set of angles? Well, here's the problem that I'm seeing. As this angle is uniquely different from these other two, I guess this would also have to be uniquely different from those other two because these are both congruent here. So if this is not congruent to, say, that one right there, looks like we're a little bit in trouble. It looks like we are a little bit in trouble. The reason why they call it angle and not angle is because once you know two pairs of angles are congruent, then the third pair of angles are congruent. Once you know that two pairs of angles are not congruent here, while one is, then the third, one is not congruent. Well, the point is L is not going to be the same as one of these. Otherwise, this would have to be the same as one of those. One pair of angles is congruent, but that's it. That's it, just by vertical angles here. These are not similar. At least we don't know them to be similar, right? We don't know if maybe this one is congruent. I'm just going to say not similar. Really not enough information, but if these were congruent here, maybe that could be congruent. Maybe. I'll just say not similar. All right, and the last set here, we do have vertical angles once again on these two here, but then we also have these markings right here, and that does not say that these segments are congruent. It says that they are parallel. And when you have parallel lines there, you seek a transversal, such as, I don't know, this one right here. And when you have, just look at green, when you have two parallel lines cut by a transversal, you do get an alternate interior angle relationship there, such that these are congruent to each other. This isn't the only set I could do. I could also do this set right here and get these alternate interior angles congruent with each other as well. Guys, I have a way of showing through angle that all three sets of these angles are congruent. I'm going to stick with angle here. Vertical angles and one pair of alternate interior angles. These are definitely similar, not congruent, but I do have two different pairs of angles that are congruent right here. Triangle EFG, going the blue single arc mark to the green arc mark to the, nothing marked there. So blue, green, do. That's EVW. So triangle EFG is similar to triangle EVW by angle. All right. Or angle, up to however you want to call that. All right, and that's it. And hey, yeah, this one doesn't have a similarity statement. They are not similar, so there's no statement to make. All right, for number 6 through 9, the triangles in each pair are similar. Solve for x, show all work. Now, in this case here, you have to, well, you can work with triangle things in any sort of way that you want. They do tell you that they are similar, so we can use that luxury of working any proportions that'll help us solve for x. And you have a multitude of options to choose from as long as you work with corresponding parts. I got to use the 9x minus 10, which is whole side of, I'll say the top. The top of the big triangle, top side of big triangle, that's going to correspond to top side of small triangle. So I can use some form of 9x minus 10 over 50. That's great. I can use that. That equals. Now I can either use bottom left side, let's say bottom left side of whole triangle to bottom left side of small. So I can do 72 over 45. I could have also used 48 over 30 because that's whole over whole right there. I'm going to go ahead and leave it at this. So this is a setup here. Cross multiplication is in the works. That's a definite possibility. Before that, these can divide by 9 over 9. So I can turn that into 8 over 5 instead before I get that cross multiplication in. If I really worked hard, guys, I could multiply these two things by 5 right here, reduce that to 1/10, reduce that to 1 over 1. I'm going to keep it like this because I think people get a little lost when I do that. So I'm going to cross multiply from here. And when I cross multiply, you get to see some other steps here as well. I have to multiply 5 with both 9x and negative 10. And here I have to multiply 50 by 8. So 50 times 8 is 400. And that gives me 45x minus 50 over here. If I add 50 to both sides and then divide both sides by 45, I will get x equals 10. I'm saving time on the algebra here, hoping that you have the algebra and you can just kind of work out the geometry, right? That's kind of the end goal. All right, so that is solving for x. Is that all I need to do? Yes, solve for x, show all work. I sure as heck did that. All right, number 7. They say the triangles are similar, so now we got to work out how this needs to be oriented to match up with this thing here. So this angle is congruent to this angle here, and then they have markings. I kind of throwing a fit with myself here, not being sure which way it actually is supposed to be faced, because here's the thing. We don't know if 3x minus 6 is a longer, I know it looks longer by the diagram, and I'm sure we can make an assumption on it. I'm going to solve this two different ways. I'll see, obviously, one way is probably going to say, oh, we didn't intend for that. They really should have marked another set of angles congruent or given us what the similarity statement is, because I don't know if this triangle here should be redrawn like this, which is probably the one where 77 is down here and 55 is up here. So that's R and S and T. Or who's to say that it's not the other way around, guys? Who's to say that this triangle isn't maybe drawn this way? This is still R, but now this is S and this is T. That means this is 55 and this is 77. Because what I always say to my students when you're trying to do these is make sure that you align parts, that you go shortest side with shortest side, things like that. I don't know what 3x minus 6 is. I don't know if it's going to represent the shorter side or the longer side. Therefore, I don't know which way the 55 goes, which way the 77 goes. I just don't know. I haven't done this before, so I'm not sure. I'm going to assume it's this top one that I'm going to do in blue first, just because the way they drew it. It looks like it's kind of drawn that way, so I'll start off with that one, but I want to see what this one looks like. I'm very curious to see how this lines up, and I'll do that in purple afterward. So 15 is to 55 is 3x minus 6 is to 77. 15 is to 55 as 3x minus 6 is to 77. This is one where I do feel like I want to tweak some bits here. Definitely want to divide by 5 on top and bottom there. I get 3/11. And yeah, if you guys are fine with this, guys, I'm going to multiply top and bottom, or I'm going to multiply both sides by 11 here. That gets these to cancel, and this turns into 1/7 right there. So 1/7. So now I have 3. 3 on the left equals 3x minus 6 over 7 on this side. You can solve however you want from there, right? The rest is algebra. I'm just giving you the setup and getting it going. Multiply both sides by 7 now. I get 21 equals 3x minus 6. Add 6 to both sides, I get 3x equals 27. Divide both sides by 3, I get x equals 9. As long as it's an integer, I feel really comfortable with that answer, obviously. We'll see what the purple one gets me. If it gets me a fraction, I guess it wasn't intended as a problem, but they have to be a lot more careful when they set it, because I didn't make this problem, so they have to be a lot more careful when they set this up. So what's going to correspond now? Now 15 corresponds with 77. This might be a mistake, because I don't know if I can reduce fractions here, but 15 corresponds with 77 now. 15 is to 77. Look, here's the thing. If you're following me on this stuff, I recommend you look at the blue. I'm going to experiment here. 15 is to 77 as 3x minus 6 is to 55. Okay, Well, the 55 and 77, if I multiply, well, I guess it's not too bad. I can work the same things as I did before, sort of. If I multiply by 11 here, I will get 1/7 here, and here I'll get 1/5. Okay, those numbers got a little smaller. That's good. Now let's go ahead and do the cross multiplication. 5 times 15 is 75. And then 7 times 3x minus 6. Guys, we got to distribute that. 7 times 3x, 7 times negative 6. I get 21x minus 42. Add 42 to both sides. You get 21x equals 117. Yeah, see, that's not a clean number there. So clearly it's not the way they intended to do the problem. But that's 117 over 21. Well, it does reduce. I can divide these by 3, and I get 39 over 7. So that's another version of the answer that you could get if indeed it says the triangles are similar, and because this is the only part that they mark congruent, I know that's the only part that corresponds. So see, I didn't know if this was bigger or smaller, but there's another possibility of an answer. Hey, it's the second answer, but I think that's the one that they wanted here. Let's leave that in purple. All right, good old time waste on that problem. Sorry about that, guys. I'm experimenting with this as much as you might need to, all depending on what you're working on. All right, let's keep moving forward, guys. This is kind of a next page, if you will. Same thing. Triangles are similar. They state that triangles are similar. We've got to do the same thing. I'm going to have to go based off appearance, I think, the rest of the way. As you can tell, one answer was clearly not intended compared to the other one here. And yeah, they really should have worked a lot better with this. We do know these angles are congruent here, so those parts obviously correspond. But hey, let's go with kind of the appearance of this. As this appears to be obtuse, let's assume that it's congruent with that. So now we can know that this side corresponds with that and this side corresponds with that. I'm just going to have to play that. I have no other option. I'm going to have to play that. I don't want to spend a lot of time on them. So let's try 27 goes to 63 and 21 goes to 21 plus x there. Right? Corresponding parts. 27 over 63 equals 21 over 21 plus 2x. Hey, do not cancel out those 21s, guys. That is not how this thing works. As long as there is addition, multiple terms there, no. Don't do that, please. But we can reduce this fraction here, divide top and bottom by 9. I get 3/7 equals, again, 21 over 21 plus 2x. I'm going to leave it. Let's go ahead and cross multiply. Let's do that right now. 7 times 21 and 3 times 21 plus 2x. So 3 times 21 is 63. 3 times 2x is 6x. 7 times 21 is 147. Subtract 63 from both sides, we get 84. And divide, you get x equals, I think it's 14. So that's solving for x there. And again, I'm just going to assume that that's the one that they chose. If I chose the other one, I feel like I'm going to get another fraction. Maybe. Maybe not. I don't know. But based on the appearance alone, I can do that. All right, this one's a little more difficult to play with based on appearance alone. I can't tell maybe if these are supposed to be, let's see, do those look parallel? Not really. Yeah, I can't tell. See, guys, once again, the problem here is I don't know whether x plus 7 is the longer or smaller side. If x plus 7 is the longer side, then it corresponds with 30, which is the longer side. But if it's the shorter side, it corresponds with 27. Based on appearance, these do not look parallel, so it is possibly more likely that this will correspond with that, as these are already congruent to each other. So maybe the same thing as last time. I'm going to try and line those up. These problems really should tell you which triangles are similar. If it said triangle FKE similar to triangle MKL, then I know for sure that that's the order. So again, kind of griping at my own worksheet. Not one that I made, but kind of griping at my own worksheet there. All right, let's do 20 to 30. Let's do the top two to the bottom two. Is x plus 7 to 27 there. 20, 30 is 2/3. Let's go and cross multiply from here, just because you probably won't have a lot of fun with my multiplying the bottom by 3. Or both sides by 3. Cross multiply, I get 54. 3x plus 21 when you distribute right there. Subtract 21 from both sides, I get 3x equals 33. Divide both sides by 3, I get x equals 11. As long as I'm getting an integer answer, I'm comfortable with thinking that that's probably the way that they intended it, even though I didn't check the other version. I'm going to go and stick with that. And again, if these were, the reason I talked about if these were parallel is because if these were parallel here, that would mean that alternate interior angles would be congruent. So then I can assume this corresponds with that, which means this corresponds with that. But they don't appear parallel, and I'm only solely going off appearance because I don't think they meant these answers to go interchangeably. I think they just messed up not giving us triangle similarity statements. All right, number 11. Use the figure below to answer the question, is TU parallel to RS? Show your work. So there's a theorem called the side splitter theorem or triangle proportionality theorem, which says if you do have two parallel lines here, then the split portion, from the segment here, the split portions would be proportional here in such a way that I could do, say, 67.5 over 54, boom, 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 is equal to 90 over 72. Straight up, set it up. Now, the converse of it says if these two are in proportion, then that means these lines are parallel. So now the question is, are these lines parallel, by checking to see if these are in proportion, right? So kind of working the other way. I don't have the luxury. I'm going to not use a calculator on this. So I'm going to refrain, and I'm going to try and reduce the fraction all on my own. So 90 over 72, I can divide both by 9, and I get 10 over, oh, I can do even bigger than that. I can do 18. 18 here, I get 5 over 4, so 5/4. We'll see if this becomes 5/4 when I do my division here. You could do a decimal shift and turn this into 675 over 540. I guess I'll do that because a lot of people might not know otherwise to say multiply them both by 2. I'm just going to do this first. Let's see what we can go from there. Let's divide by 5. Oh gosh, 120, 130, 135. Maybe I shouldn't have done this. I think it's 130. I'm going to guess 135. 135 over 108. I know that's 108. And I can divide these by, oh, what is that? 27? Yeah, 27. So if I divide top and bottom by 27 here, I do get 5/4. 5/4 equals 5/4. So again, it's me not using the calculator. If you use a calculator, you divide this. 5/4 is 1.25. So you get 1.25 here, 1.25 here. It checks out. This is me kind of saying I'm not going to use it if I don't have to. 5/4 equals 5/4. Therefore, yes, TU, segment TU is parallel to segment RS. That is what we looked for. If these weren't in proportion, then it's not parallel. But they are. Green check. All right, a bit of a word problem, and my class didn't do too many word problems with similarity and right triangles, but it's really working things out. Or in triangles, I should say, not necessarily right triangles. Use the figure out right. A person in a tree casts a shadow at the same time of day. What is the height of the tree? Round your answer to the tens place and make sure to show all your work. So I might use a calculator here. We'll see. But here, guys, it's all about similarity, right? If the sun is casting, a green sun, is casting these shadows, that means that the sun ray is hitting this thing the same way that it's hitting this thing right here. So in essence, you have similar triangles because the shadow grows. If my shadow was twice as long as me, the tree's shadow will also be twice as long as it. That's the idea behind this similarity. You don't see triangles unless you talk about the sun ray doing that kind of thing right there. So anyway, based on this right here, whatever the similarity ratio is, however many times my shadow is compared to me, this shadow will be that many times compared to this kind of thing. So if this is some sort of h, height of tree, I can say the height of the tree over 76, the shadow, the 76-foot shadow, equals my height, which is 5.6 feet, over my shadow length, which is 9.2. It's basically the setup of that thing. Yeah, you know what? Let's get some. I can reduce this. I got this. 56 over 92 can divide at least by 4 each. So if I get 56 divided by 4, that's 14. 92 divided by 4 is 23. So 14 over 23, h over 76. That's not much smaller. 14 over 23. If I cross multiply, oh man, I'm not gonna have fun with that. Okay, yeah, let's go to calculator in a second. So 23h equals 76 times 14. I don't know what that is. And then I divide both sides by 23 here, and I'm gonna get the thing. Yeah, I have a little bit of hubris, guys. A little too much pride. Do things for the sake of doing it sometimes. My bad. So if I go to the calculator, I'm gonna do 76 times 14. I sure hope I have the rest of my numbers right here. My bad if I don't. Divided by 23. The proportion is the most important part for me. All right, I'm getting 46.26. 46.26. So I'm going to round that, as I said, round to the nearest tenth of a foot, or tenth place. So that's 46.3 feet there. That seems about appropriate. The height of the tree is about 46.3 feet. All right, let's find the length of each segment here. It's a little more side splitter theorem like you saw before, or, all depending on what's there. We got to find the length of KL. I'm going to go ahead and just call it X. For this unknown side splitter theorem, once again, I could do like 4 over 6. Because, oh, by the way, because these lines are parallel. Because these lines are parallel, I can say, hey, something like 4 over 6 equals x over 8. And without I don't think I need to reduce that fraction here. These are pretty small. 32 equals 6x. Well, now I'm going to have to. When I divide by 6, I get x equals 32 over 6, which, hey, divide those by 2, I get 16 over 3. That's an exact value for x right there. All right, we got to find the length of xz right here. So if I put x here, here's where you got to be careful. Because if I do something like x over 30 as one of my proportions, boom to boom, I got to make sure I do boom to boom right here. And this guy right here, the whole thing is 30, but not the little guy right here. What is this length? I got to do 30 minus 18, which is 12. That'll help me get this little guy right here, and that gives me like 12 over 18 that I want. See, that's where you just got to be careful. Make sure you correspond parts in that it's a whole side of small left part of triangle, whole right side of small part of triangle. You know what I mean. Work that thing out in such a way that can't be 30. That doesn't correspond with x, or my unknown that I'm looking for xz. All right, before I cross multiply, I do want to reduce this fraction. This does reduce to 2/3 because these numbers are just a little bit larger. And let's go ahead and we go 60 equals 3x. Divide both sides by 3. You get x equals 20. Hope I'm not going too fast, and also I definitely hope I'm not going too slow. Or I hope this pace isn't too slow for you guys. Finally, length of VM. X here is just that length. And one more time, guys, 49 is apparently that whole side. If you wanted to go about it in another way, if you don't know the side splitter theorem, if it doesn't make sense to say this divided by this is this divided by this, and if you understood more just about the similar triangles, by the way, these triangles are similar. Reflexive property makes this congruent. Parallel lines make corresponding angles congruent. Angle, angle. So triangles are similar. That's why the side splitter theorem works. Anyway, if you're more convinced with, or if you understand your triangle similarity stuff more, and you got to do whole side and whole side here, you can turn this into x plus 8. Whole thing's x plus 8. So here I could say x over x plus 8. Whole side of smallest to whole side of big as whole side. Oh, hang on a second. I don't have. Sorry. Let's do this. You know, am I making it too complicated? Yeah, let's try it. Let's try it. Let's do x over x plus 8. But now I guess I do got to get this number still. That's going to be 35 equals what? This will be 35 out of 49. Notice what I did here. X over x plus 8 equals 35 out of 49. I went whole side of small to whole side of big on both of them. It's just another way of setting it up that, you're going to get the same answer no matter what you do. You just got to kind of find your niche. If I divide these by 7, I get 5/7 here. 7 over 7, I should say. I get 5/7. Cross multiply, I get 7x equals, as this distributes, 5x plus 40. Subtract 5x from both sides, I get 2x equals 40. Divided by 2, I get x equals 20. If you had your own way of doing it, you're totally fine. You should still be getting x equals 20, assuming you get everything else taken care of. All right, we're halfway through pages-wise, and that's about half an hour through. So let's see if I can finish this within the hour. Moving along here. Now we're dealing with right triangles. I think the rest is kind of right triangle-esque. For numbers 16 and 17, find the values of x, y, and z. Give exact answers in simplest radical form. These problems look eerily familiar to something I've given before, but that's okay. All right, let's start with y, because I can use Pythagorean Theorem to find y by knowing this is a right triangle right here, and I'm given a leg and the hypotenuse. So I know that y squared plus 25 squared equals 65 squared. Notice they say simplest radical form, by the way. There's a possibility we have to simplify some radicals. That's y squared plus 25 squared is 625. 65 squared, I do not know. I know. Wait, so 64 squared, 4,096. Oh, I think it's 4225. Let's see. 65 squared, yeah, 4225. 4,225. So subtract 625 from both sides, you get 3,600, and take the square root of both sides, you get plus or minus. Oh, hang on, take the square root. You get plus or minus 60. Now, because it's a length, it's really just going to be positive 60. Right, just positive 60, and that is the value of y. The reason I chose y to get y first is because I can now use this number to help me get x and z as needed. I don't know if I could have gotten. Hang on. I don't know if I could have gotten x or z without getting y first. So Pythagorean Theorem me this. Because we haven't yet spoken on geometric means, I don't know if I want to speak on it just yet here. It's fine. I'll speak on it both ways here, guys. If I wanted to solve for, let's see what I want to solve for here. X. if I want to solve for x here, I could say in the small right triangle here, I can do short leg of a small right triangle is to the short leg of the medium right triangle, as the long leg in the small right triangle is to the long leg in the medium right triangle, like that. Equivalently, you guys might remember that 60 is the geometric mean of 25 and x. So you'd set up the same thing. 25 over 60 equals 60 over x. We'll do more of that later, but setting this up is kind of equivalent. Reduce fraction, I get 5/12. Cross multiply, not much room here, huh? I get 5x equals 720. Divide both sides by 5. I get x equals 144, I believe, 144. So y is 60, x is 144. Now we need z. You have everything under the sun if you want to solve for z using similarity, but you can also use Pythagorean Theorem, and always use what's most comfortable for you. For me, well, I guess Pythagorean Theorem is still most comfortable. I just don't like the big numbers in general. But for z, let's use a different color because it's getting a little colorblind. I'm going to use, here's my right triangle I'm looking at. You could use the huge one. I'm just going to do this kind of one right here. Z is the hypotenuse, opposite that right angle. So 60 squared plus 144 squared equals z squared. Let me just compute all that all at one. That's 3600 plus 144 squared. Okay, that gets me 24336. Z squared equals 24,336. Take the square root of both sides, guys. You get z equals, what's the square root of 24,336? Square root of previous answer, it's 156. So z is 156 right there from using Pythagorean Theorem. You could do the similarity thing as well, but there's your third and final answer. All right, number 17, find x, y, and z, kind of the same fashion as before, only now it's a different setup. This time, guys, x literally is, x is the geometric mean of 30 and 40. That means that 30 times something is x times that same number is 40. What is that x in between that makes that happen? Not what is the number that you multiply by. But I can do 30 over x equals x over 40. 30 over x equals x over 40. That is the geometric mean principle that we are actually going to use, I think, in the top of the next page here. Anyway, cross multiply, we get x squared equals 1200. And then take the square root of both sides, guys. Here's where you got to do some radical simplification. No plus or minus, but 1200. I can break that up and say 403. 400 times 3. I chose 400 because the square root of 400 is 20. If you didn't know that, you could probably choose 112 to begin with, because you should know the square root of 100 is 10, or at least just know that 100 is a perfect square. This will get you 20 root 3. Sorry for running to this guy and his kite. But 20 root 3 is a simplified radical. No approximating by decimals there. Still got to know how to simplify radicals at this stage. If you want to solve for y and z, guys, it's a Pythagorean theorem thing the rest of the way here. For y, that's the hypotenuse, where I can do 30 squared plus 20 root 3 squared, equals y squared. So that's 900 plus, hey, what's 20 root 3 quantity squared? Well, 20 squared is 400, root 3 squared is 3, 400 times 3 is 1200. Hey, we've seen that number before. That number squared, 1200, right? So 900 plus 1200, that's 2100. Take the square root of both sides here. This time I'm going to work with that 100. 100 and the 21. Yeah, 21 doesn't have any perfect squares. So it looks like that's going to be 10 root 21 right there. All right. Last one for z here. Let's use 40 and the 20 root 3. Definitely running out of room. Let's use a different color again. 40 squared plus 20 root 3 quantity squared equals z squared. 40 squared is 1600. We know this one is 1200 equals z squared. Oh my gosh, running out of room. Z squared equals 2800. I can divide that by 400 again, just like or factor out the 400. So z is the square root of 2800, which is root 400 times root 7. 400 times 7 is 2800. So that'll give me 20 root 7. That is a 7. Right there. That's my final answer for that one. 20 root 7. And we're off. These problems do look familiar. I think I gave those. No, what's weird is... Yeah, I'm not going to talk about it. All right. Well, yeah. Okay, so what's weird is I thought I made those problems from... I thought I crafted them from a... That's okay. Don't worry about it. All right. Number 18. In the figure at the right... Sorry about that. Stan is flying a kite at the end of a string that is 350 feet long. There's the string. There's the kite. There is white boy Stan. He's letting go. There goes the kite. Stan is holding the string 5 feet off the ground. So, hey, this, guys, this is 5 feet. And here's a principle we can apply. This is a horizontal line. The ground is also horizontal. That makes these parallel. That also means, guys, this is 5 feet. We might use that later. But your right triangle is this thing right here. This is what we need to focus on right now, just the right triangle. Just letting you know that if one part's 5 feet, the other is. Anyway, let's keep going. So 5 feet off the ground, an angle to the horizontal. How, as shown, so 23 degrees with an angle to this horizontal right there. How high is the kite off the ground? Round your answer to the nearest tenth and show all work. So now we're getting some of the trig here, guys. We have some trigonometry. We want to figure out how high this thing is off the ground. So I'm going to place an X right here. It's important for us to figure out how high this portion is inside the right triangle. And here's the thing. Whatever X is, we're going to add 5 to it because this is the right triangle, which is levitated 5 feet off the ground. So we have to add an extra 5 feet ultimately because they're asking how high the kite is off the ground, not from Stan's hand, not like a point that is parallel to Stan's hand right there. So let's solve for X in the right triangle here, guys. We do have, if we use SOHCAHTOA, if we use the concept of SOHCAHTOA to determine whether you're supposed to use sine, cosine, or tangent, relative to the 23-degree angle, we are looking for the leg opposite. And we know the hypotenuse. Opposite and hypotenuse should use sine. So we're going to take the sine of 23 degrees. And this is where we have to use a calculator, by the way. Sine of 23 degrees is opposite over hypotenuse. That is our setup. Now I can multiply both sides by 350 to get X by itself, right? So times 350 on this side times 350 on this side. And we will get X equals, as an exact answer, 350 times the sine of 23 degrees. All right, so there's the setup there. Now let's go ahead and calculate this. So when I use my calculator right here, I need to make sure that here are my calculations from before. I need to make sure that my calculator's in degrees. Mine is actually in radians right now because the simulator always resets each time. So, because we're doing degrees. So I'm going to do 350 times the sine of 23 degrees. And this will be the height off that horizontal point. So that's 136.75. They want to do it to the nearest tenth. So I'm going to take that and round it to 136.8 feet. It's not my final answer, though. Not my final answer. My final answer, if I wanted to find height, remember that is the entire thing to here, including the 5 feet. So the height takes the 136.8 and adds 5 to it. And that is 141.8 feet off the ground. That is the final answer right there. Now, I did something that I normally don't do, and I'll not do later. I was just so excited to use the calculator here. I really should have put +5 right here and then computed this all as one. Reason being, I rounded something early before doing a future calculation, and I warned my students never to do that. I kind of forgot that and stuff. So anyway, about 141.8 feet because the extra 5 feet added. Kind of different from the ones I've done with my students because they didn't get the extra part, but because it was drawn for you, I'm kind of comfortable having you see that. All right, number 19. Find the measures of angle J and L to the nearest tenth of a degree. Show all work. So I need to find out this angle right here. Let's start with J. Knowing only 8 and 17, which if you use Pythagorean Theorem, you could find out, hey, that's 15, and go there. But let's say we don't know that. Let's say we don't bother with that. Or special right triangles, I should say. So 8 and 17 here relative to J. 8 is the adjacent leg to J. And 17 is the hypotenuse of the right triangle. In SOHCAHTOA, adjacent and hypotenuse is reserved for cosine, right there. So I can take the cosine of the measure of angle J, Mr. J, and I get 8 over 17. The way to get measure of angle J by itself is I need to take the inverse cosine of both sides, which will cancel out cosines there, and inverse cosine of that side. So the measure of angle J is the inverse cosine of 8/17. I'm going to go ahead and compute that. There's nothing else to be careful of there. So let's go ahead and take a look at that one. My inverse cosine function's right there, 8/17 right there, and I get 61.927, so 61.9 degrees. Measure of angle J is about 61.9 degrees there. That is my result for J. L, you can get L in one of two ways, guys. If you really wanted to just go like, hey, I know what's going on with this stuff right here. The measure of angle L is the complement of the measure of angle J. It's 90 minus the measure of angle J. So I could just do 90 minus 61.9, which is going to give me 28.1 if I did that right. So it should be that. Now, if you don't know how to do that, if you don't understand why it's its complement or the fact that they add to 180, if you have no thought of that, why don't you use some trig to determine that? So let's check that out. 8 is opposite of L, and 17 still the hypotenuse. That is using sine, opposite over hypotenuse. So the sine of the measure of angle L equals 8 over 17. And if I take the inverse sine of both sides, I'm going to get the measure of angle L equals the inverse sine of 8 over 17. If I apply that in the calculator, I should be rounding to 28.1. Let's see what we get here. The inverse sine of 8 over 17 gives me 28.07, which rounds up to 28.1. So the measure of angle L is about 28.1 degrees. Not Fahrenheit, nothing like that, just 28.1 degrees. All right, that is it for that problem. All right, number 20, solve for x, round in the nearest tenths, show all work. This is, x is not the hypotenuse. Some people believe that because it's slanted, it is. Remember, the hypotenuse is always opposite the right angle. This is the leg adjacent to the 29 degrees here. This is the leg opposite the 29 degrees. TOA, tangent, uses opposite and adjacent there. So we are going to be taking the tangent of our angle. Let's take the tangent of 29 degrees, and we will get opposite over adjacent, 22 over x. The next step or steps is algebra. If I multiply both sides by x, I get it in the numerator up here. If I divide both sides by tangent of 29, I get it in the denominator down here. It's really a thing of them switching places. Again, if you haven't watched any of my other videos, this might be a little much for you. Do it however you need to algebraically. Just get x by itself in the numerator. This will become x equals 22 over the tangent of 29 degrees. This is something I have to compute. Make sure your calculator's in degrees, as mine still is. So 22 divided by the tangent of 29, and I have no idea what number I'm going to get. 39.689. They said round to the nearest tenth. That'll be 39.7. So x is about 39.7. Is this degrees? Heck no, this is a length. So this is a length. Is it feet? Well, no, it's non-contextual. It's just about 39.7. That's all they wanted. All right, numbers 21 through 25, find the values of x and y, give exact answers, no calculators or decimals. So while trig is an option, it's not so much so if I want some exact answers, meaning possibly radicals in the way. No rounding to anything, as this is an irrational value, guys. That number does not ever repeat, but it goes on forever. It goes on forever and never repeats as a decimal. So irrational. These ones need to be with radicals if need be. So in a 45, so here's a 90-degree angle. This is 45. This also must be 45. This is a 45, 45, 90 right triangle. A special right triangle in such a way that in every 45, 45, 90 right triangle, the hypotenuse is always the square root of 2 times larger than either leg. So if I wanted to figure out the length of one of these legs, such as x here, I got to divide 20 by the square root of 2. So x is going to equal 20 over the square root of 2. Now simplified, we need to rationalize the denominator, which means I got to multiply top and bottom by root 2 just to turn the bottom into a 2. I need to rationalize it. So the bottom becomes 2. Awesome. The top is 20 root 2. Well, I can still, now I can reduce this. 20 divided by 2. This becomes 20 divided by 2, which is 10. So that gives me 10 root 2. That is x's value. A 45, 45, 90 triangle, or right triangle, is isosceles as well. Whatever this length is, this length is. These are congruent. These will be equal to each other. So y also equals 10 root 2 because x does. So those are both of your values. Again, whatever x is, y is. All right, let's take a look at this one. It's oriented the same way here. It's another 45, 45, 90. So we just talked about how x should be, the leg length should be the same. So I already do know right off the bat here, x is indeed 23. X is 23 right there. And the hypotenuse is root 2 times larger than either of these. So if I take 23 and multiply it by the square root of 2, y becomes 23 times the square root of 2. That cannot simplify any further. I am actually done with the problem. That's it. No more. Yeah, so you're going to hear those probably a couple times more. This is a 30, 60, 90 right triangle. A little more peculiar when it comes to determining what's what. You know, what you place where and such. X, if this is considered the shortest length here, the hypotenuse is actually twice as long as the shortest leg opposite the 30. So if I want to figure out what x is here, I got to take the hypotenuse length and divide by 2. So over 2 here. So x, whoa, sorry for the glitching. It's not my doing. This thing just does this sometimes. I never figured it out. X equals 21 over 2. I'm not going to write 10.5. Not that it's not exact. I'm going to leave the exact answer. Let's leave the exact answer. In fraction form, improper fraction form. From shortest leg to longest leg, opposite the 60 here, you got to multiply by root 3. So yeah, mincing no words here. Y is 21 root 3 times root 3, all divided by 2. And really, that's it. There's nothing else we can simplify this. No radical, no fraction to reduce, no radical denominator to rationalize, no radical to simplify, nothing like that. We're done. It looks like 24 and 25 are, more of the same here because they said 21 to 25. So here's another 30, 60, 90 triangle here. 30, 60, 90. And 9 is the leg opposite the 60-degree angle. That means it's the long leg, which is the square root of 3 times larger than x. So to get x, I have to divide by the square root of 3. So x is going to be 9 over the square root of 3. If I rationalize the denominator, then I'm going to multiply top and bottom by root 3. So that'll give me 9 root 3 all over 3. 9 over 3 is 3. That gives me 3 root 3. Are you sick of me saying 3? All right, that is x. Y, being the hypotenuse opposite the right angle of this right triangle here, is twice as long as the shortest leg, which is 3 root 3. So y takes the 3 root 3 and double. I wrote 2 already. Y is the 3 root 3. You take that and you double it. Multiply by 2. 3 multiplies by 2, not the root 3. That becomes 6 root 3. Awesome. There we go. 3 root 3 simplified, and then this becomes 6 root 3. All right, last problem. Whew, looks like they have a little thing going on here. Gosh, where do I start? Well, this doesn't have any side lengths provided yet. They share a side here, which is awesome. Once I get this, it can help me find that. We need to find both x and y. Here's a 30, 60, 90 triangle here. Looks like I need to get the short leg by knowing the long leg here. I get to divide 7 by the square root of 7 root 3 by the square root of 3. Guys, here I'm going to get 7. There I'm going to get 7, right? Now, here to get to the hypotenuse of this guy, I need to multiply by 2, right? The 30, 60, 90 is 1 to 2 to root 3. So multiply 7 by 2. X is 7 times 2, which is 14. Nice and clean number. And y, being in a 45, 45, 90 triangle, understanding that if this is 7, then this is also 7, right? The hypotenuse is the square root of 2 times larger than either of these. So y is 7 times root 2. And it's just going to stay like that. So there's x at 14. There is y at 7 root 2. And that's it. Probably the easier of the math things to do on those problems, even though it was a little trickier as far as what to look at. Hey, we have 5 more problems left. Here we go. 10 more minutes before the hour ends. For numbers 26 to 28, find the geometric mean of each pair of values. Write all final answers in simplest radical form. So the geometric mean of 2 and 18, again, says that there's a number between 2 and 18 in a geometric sequence. It means that 2, some unknown number, and 18. I multiply 2 by something to get x. I multiply x by that same something to get 18. What is that number that's going to be in the middle? You guys might know, but you have to really also be careful. There is more than one answer. We do 2 divided by x, and that's going to be the same thing as x divided by 18, or 18 over x is the same thing as x over 2. It doesn't really matter. When you cross multiply here, we get x squared equals 36, and when you take the square root of both sides, you get x equals, plus or minus 6. Yes, there's more than one answer. There is no distance here being covered, so these values are allowed to be negative. That's one of them. Let's keep setting these things up. 3 over x equals x over 9. Doesn't get much trickier than that as far as setup here. Cross multiply, we get x squared equals 27. Take the square root of both sides. X is plus or minus. I got a root 9 times root 3, and I choose root 9 because I can take the square root of 9. That gives me 3, so this will be plus or minus 3 root 3. Hey, we got an x equal 3 root 3 before. Look at that. Only now it's plus or minus. You betcha. All right, number 28, we got 20 and 27. Hey, 20 over x equals 27 over x. Oh, sorry, equals x over 27. That would have been wrong. Equals x over 27. If I cross multiply, I get x squared equals, 20 times 27, 540. Wait, yeah, 540. I got to take the square root of both these, and I get x equals plus or minus. Oh, what can 540 get in with? 99. You can do 9. Well, here's the thing. It was 20 times 27, right? So why don't I first split it up into root 20 times root 27? Because I know root 20 is root 4 times root 5. And 27 is root 9 times root 3. Heck, it's 3 root 3. We just talked about that. So root 4 is 2. Root 9 is 3. And now we get to multiply rationals with rationals and irrationals with irrationals. We'll get x equals plus or minus 2 times 3 is 6. And root 5 times root 3 is root 15. Make sure the root 15 can't simplify any further. It cannot. There is no perfect square factor that exists inside there. And I'm good to go. So that's just me working a little bit, off the bigger number there. You can do a lot of different ways to figure that out once you kind of do it. Maybe it could have divided by 16. I'm thinking, no, I don't think it could have. I don't know what the biggest, the biggest number was 36 apparently. Anyway, 36 times 15 apparently is 540. All right, 29. This is one of my questions. The Tower of Pisa was originally built 60 meters tall, but after leaning, its altitudinal height with the ground now measures 59.85 meters tall. What is the angle that the Tower of Pisa makes with the ground after leaning? Round your final answer to the nearest tenth of a degree. So a word problem with a bit of a diagram to kind of assist you on the idea of the leaning Tower of Pisa here. So as it stood to begin with, guys, it was originally 60 meters tall. That means that this height that you're looking at right there in blue, that's the 60 meters that we get to talk about right here. Is this perfect? No, probably part of it sunk into the ground. Let's just go based off the idea of the drawing. Now it's altitudinal height with the ground after leaning. Like if someone said, hey, how tall is that? Just looking straight up, guys. This part right here, this is the 59.85 meters. Now, this is a small right triangle right here, right? It's slim. Very, very slim. And now they're asking, or I'm asking, what is the angle that Tower of Pisa makes with the ground after leaning? So now that it's leaning, what is this angle? What's this angle right here? I'm going to call x. All right. I want to know what that angle is that it's making. So this is opposite and hypotenuse. This is opposite and hypotenuse. The sine of our unknown angle equals opposite over hypotenuse. So take the inverse sine of both sides. We're going to go ahead and compute that right there. It should be a number. Look, it should be close to 90 degrees. It's not leaning that much, otherwise it'd be dangerous to kind of go into. It probably would have fallen over by now. It's going to be close to 90 degrees. Right, let's take a look. Nearest tenth of a degree. Let's see what it gets to nearest tenth of a degree here. So let's go ahead to the old graphic calculator. Let's take the inverse sine of 59.85 divided by 60. Our answer will be in degrees here, by the way. 85.94. Rounded to the nearest tenth, that is 85.9. 85.9 degrees right there. So there you go. 85.9 degrees is that lean. Right there. Not quite a 90. About 4 degrees lean. You know what I mean. What about 4 degrees? All right, last question, find the missing length. I wanted to make sure to throw in one of these in a for sure way where there's no geometric mean involved. Heck, you could do geometric mean if you use Pythagorean Theorem to find this length. I'm going to refrain from that. Let's see if we still know how to do all the triangle stuff here. I do have a small triangle where I know the short leg of 1 and the hypotenuse of 2. Short leg of small, hypotenuse of small. Then I have the big triangle right here where I also know the short leg of 2 and the hypotenuse, sort of, 1 plus x. Right? 1 plus x right there. So I want to do short leg to short leg of small to short leg of big equals hypotenuse of small to hypotenuse of big. Okay, there's a setup in that form. Without no Pythagorean theorem, no geometric mean, just straight to war. Cross multiply here, I get 4 equals 1 plus x times 1 is still 1 plus x. And subtract 1, you do get x equals 3. There it is. All right, guys, I did finish within an hour. I feel so accomplished with that. That ought to do it for me. This is Mr. Robinson. Thank you for checking this out. Catch you in the next video, which I don't know what it's going to be. I got to make one for my IM1 classes, but this is kind of it for my IM2 classes here. Catch you later. Thank you.